Welcome back to Introduction to Symbolic Logic. This is lecture 10. We are going to leave behind TFL now and move on to discuss FOL. That means that we are going to start to construct an entirely new formal language. This is how we are going to proceed today. We are first going to discuss the building blocks of FOL, meaning the symbols that go into this language. Then we are going to discuss how you can construct formulas and sentences using the basic FOL symbols. And then we are going to approach the topic of truth. So we are going to discuss how FOL formulas and sentences are interpreted, and specifically what an FOL interpretation is. And then we are going to discuss truth on an interpretation, meaning the conditions under which FOL sentences are true on a given interpretation. And then in the final part of the lecture, we are going to consider why some quantified sentences sound false, even though strictly speaking they are true. So that's what we are up to today. Let's start with FOL syntax, and in particular with the basic building blocks of FOL. You may recall that the smallest syntactic units in TFL are whole sentences, which we symbolized by means of capital letters. So we chose capital letters to represent atomic sentences, and then we learned how we can construct complex sentences out of these atomic sentences. So the small syntactic units are entire sentences. Now FOL is different. The smallest syntactic units in FOL are not whole sentences, but names and predicates, which we can then use to construct sentences. Why do we do that? Why do we introduce names and predicates? Why don't we just stick with TFL? Well, the short reason is that there are some arguments which appear valid, but TFL doesn't allow us to explain why they are valid. So here's an example. Willard is a logician. All logicians wear funny hats. Therefore, Willard wears a funny hat. Now this argument seems clearly valid. If Willard really is a logician and all logicians wear funny hats, then yeah, true, Willard wears a funny hat. It seems impossible for both premises to be true and the conclusion to be false. Now, the issue is that TFL represents both premises and the conclusion simply by a capital letter. So both premises and the conclusion are atomic sentences, so we would represent them as, say, A, B, therefore C. But if you look at this argument, A, B, therefore C, there's no formal or structural reason why this argument should be valid. So TFL and the kind of symbolizations that we are able to execute in TFL does not allow us to explain why the argument from P1 to the conclusion C is valid. Now, FOL is more fine-grained. FOL allows us to describe the internal structure of sentences, and this will allow us to explain why this argument is valid. So let's look at the basic building blocks of FOL. FOL has 6 basic building blocks. First, we have the Boolean connectives that we have already encountered. So we have the negation sign, the conditional, the biconditional, the conjunction sign, and the disjunction sign. Then we also have bottom, which we have already encountered, the symbol representing a contradiction. Next, we have names. That's new, we didn't have names before. We will represent names by means of lowercase letters from the beginning of the alphabet. So A, B, C, and so on and so forth. Next, we have predicates, and we are going to represent predicates by means of capital letters such as F, G, H, and so on and so forth. And then we have quantifiers, in particular the reversed E and the upside down A. I'm going to explain more what these are in just a couple minutes. And we have variables. And variables are going to be represented by lowercase letters taken from the end of the alphabet. So X, Y, Z, and so on and so forth. Now, this is just an overview. I will talk about most of this in more detail in what follows. So let's talk about names. Names refer to objects. So for example, Vera, my name, refers to me. Paul refers to Paul, and so on and so forth. In FOL, we symbolize English names by means of lowercase letters with or without subscript. So for example, A, B, C, A subscript 5, B subscript 19, and so on and so forth. These all represent names. As a special case, we also use numerals to refer to numbers. So we use the numeral 5 to refer to the number 5. Now, FOL simplifies certain aspects of English. And here I want to emphasize two simplifying assumptions that we are making. In English, names can designate multiple objects. So for example, you may know more than one Paul. So the name Paul may refer to more than one person. And you may need to consider the context to find out which Paul is being referred to. Now in FOL, we will assume that every name designates exactly one thing. So we will rule out that, say, the name A refers to more than one thing. That's our first simplifying assumption. Now, the second simplifying assumption concerns empty names. In English, names may not refer to anything. So, for example, Harry Potter doesn't refer to anything at all. Or maybe a fictional object. To give a different example, Pegasus doesn't refer to anything at all. The flying horse from Greek mythology doesn't exist. Now, we will, however, assume that every FOL name designates something. So if you see an FOL name, say A or B or C, you can assume that this name refers to something and is not an empty name. So these are our two simplifying assumptions about names. Next, let's talk about predicates. Predicates refer to properties. So for example, green or is green is a predicate, and it refers to the property being green. We symbolize English predicates in FOL by means of capital letters, which again may or may not be subscripted. So for example, F, G, H, F subscript 2, H subscript 11, and so on and so forth. All of these are FOL predicates that represent English predicates. Now, predicates can have one or more so-called argument places. So for example, is green is a one-place predicate, meaning that you need one name and combine that one name with the predicate is green to form a complete sentence. So for example, the tree is green is a complete sentence, and here I have taken just one name, the tree, to supplement the predicate is green and was able to form a complete sentence in this way. Is a sibling of, on the other hand, is a two-place predicate, meaning that you need to use two names and combine these two names with the predicate is a sibling of to form a complete sentence. So for example, the sentence Anna is a sibling of Bill is a complete sentence, and here we have used the two names Anna and Bill and combined them with the predicate is a sibling of to form the sentence. Now there are also 3-place, 4-place, 5-place predicates, and so on and so forth. The important point here just is that predicates may have one or more argument places. Now we will again make a simplifying assumption. English predicates often are vague. So for example, consider the predicate is bold. In some cases, it may be unclear whether a person is bold or not. They may have borderline many hairs on their head, and you may say, yeah, kind of bold, kind of not bold. It's not quite clear. Now, we will assume that every FOL predicate is non-vague, meaning that for every FOL predicate, it is always entirely clear whether an object satisfies that predicate or not. We have one special predicate in FOL, which is the identity predicate. The sentence A equals B in FOL says that the objects A and B are identical. And by that we mean that they are one and the same thing. So when we say A equals B, we do not merely mean that they look alike, or seem to be the same, or are very similar. We really mean that they are one and the same object. So in particular, A equals B is true if and only if the two names, A and B, refer to the same thing. Now we have special notational conventions for the identity sign. In particular, unlike other predicates, the identity sign may appear between names or variables. So as we have just seen, A equals B is a complete sentence. Other predicates always appear in front of names, not between them. And we can represent negated identities in two ways. You may take an identity statement and just prefix it with a negation sign, and that results in a negated identity. Or alternatively, you may just cross out the identity sign. So these two sentences on the right-hand side there, they say the exact same thing. They both say that A is not identical to B, meaning that the two names A and B refer to different things. Next, let's talk about quantifiers. English quantifiers are words like some, all, any, every, many, most, and so on and so forth, that we can use to indicate a quantity. In FOL, we will focus on just two quantifiers, meaning the existential quantifier, represented by the backward E, and the universal quantifier, represented by the upside down A. And we want to use the existential quantifier to represent the English word some, and the universal quantifier to represent the English word all or for all. So let's look at some examples. Consider the English sentence, some chickens are brown, and suppose we represent the predicate is a chicken by means of the capital letter C, and the predicate is brown by means of the capital letter B. We can then symbolize the English sentence, some chickens are brown, by means of the FOL sentence, there is an X such that CX and BX. So some X is both C and B. Or consider the second English sentence here, all students are bright. If we represent the English predicate is a student by means of the capital letter S, and the English predicate is bright by means of the capital letter B, then we can represent this English sentence in FOL using the universal quantifier by saying that for every X, if X is a student, then X is bright. Variables are a lot like names. So like names, variables also refer to objects. But unlike names, variables do not refer to specific objects. So for example, the variable x refers to an arbitrary object in our domain. And when I say some x is f, I do not say that a specific object is f, but rather I say that some arbitrary object in our domain is f. In FOL, we represent variables by means of lowercase letters taken from the end of the alphabet, and these lowercase letters may appear with or without subscript. So for example, x, y, z, x subscript 5, y subscript 27, and so on and so forth. All of these are variables in FOL. Now, when you look at a quantified sentence, you're always going, well, not always, in most cases, you're going to see multiple occurrences of a given variable. So for example, in the sentence here, you see three occurrences of the variable x. There is an x such that cx and bx, and here the different occurrences of the variable x play importantly different roles. The first occurrence belongs to the quantifier. So the reverse e by itself is actually not a complete quantifier. Only the reverse e together with the variable x is a quantifier. And now the second and the third occurrence of x belong to the open formula that's embedded in the scope of the quantifier. So what this sentence says is that there is some x such that cx and bx, and the first occurrence of x belongs to the quantifier, and the second and third belong to the formula embedded in the scope of the quantifier. Now you may wonder, why do we call FOL FOL? Where is this name coming from? FOL variables, x, y, z, and so on and so forth, range over objects, meaning things like dogs, cats, chairs, numbers, and the like. So that's why we call FOL FOL, which stands for first order logic. In second order logic, the variables also range over properties of objects. So in second order logic, we may have variables that range over properties such as being green, being tall, being funny, and so on and so forth. Now, since in FOL, the quantifiers bind only variables that are restricted to things of the first order, so to speak, to the exclusion of properties and properties of properties, and so on and so forth, that's why we call FOL the language of first order logic. Okay, next we are going to discuss how we may use these FOL symbols to form FOL formulas and sentences.